Okay, so in this tutorial, let's continue with the previous tutorial where basically I explained to you a bunch of different latencies and connections between all of these architectures. But what I want to do in this tutorial is to show you a real example. So let's say that we have an e-commerce store, and that e-commerce store, let's say that e-commerce store is a multi-tenant store. What this means? Well, first of all, let's explain what is a multi-tenancy application. Multi-tenancy application. So it means that you can have multi-tenants. What is a tenant? Tenants is like, let's say that you have e-commerce tenants. It means they can have multiple e-commerce stores inside. So maybe you can have e-commerce for some country, like for US, and you can have another e-commerce for UK. But all of this, it is the same software. The difference that the information, the data that appears in each of these stores, it is different. So you can have the products that you are selling in this e-commerce, you only have products for US and you only have products specific for UK. So this is a multi-tenancy app. So let's say that you have something like similar like this. So what do we want to do? So let's say that the clients you have in the client, it could be a browser just to make our life simpler. So the client will talk via HTTP to us. If you use, you can always use React, and in some type of cases you can even use WebSockets also. But let's just keep this explanation a little bit easier. So let's say that the client will talk with the DNS to get. So the client will have a bunch of URLs. Let's say that we'll have the URLs, and we'll have the URLs to get the products. We'll have another URL to get the products one or whatever. Then we'll have another URL to register user. To register user, to get the details of the user, to do the specific purchase of his cart. So card purchase or payment, whatever. Let's say that you have a bunch of these URLs. So then I can tell you that, okay, so if the client, so we can configure, so then the client will connect with the DNS, with the correspondent DNS, and in here the DNS is configured based in geolocation. So if client is from US, it will return the CDN in US. If the client is in Europe, the CDN, it will return the CDN from UK. Something like this, whatever. Okay, then this will not return, so it will return the CDN IP. It will return the CDN IP. So something like this. So the client will have is the same URLs, but when it connects with the correspondent DNS according with the location that he is, automatically you get different IPs. So then, when the request gets to the correspondent CDN, let's say that, like examples, very simple examples. Let's say that these two requests, they have cache. So for these two requests, so let's put here something like this. Okay. So if there is cache, then return it right away. So we are talking about here, we are talking less than 300 milliseconds. Well, it's not quite like this, because depending of the data, then we need to have here the length of the data. If you have then images maybe it will have another TCP request depending of the URL of the images, if they are in CDN or if they are in some other server, if they are in your data center, if they are in some third-party API. So it's a little bit less than that, but they are workarounds that you can have. So you can have always, like, you can load first some default images and then replace that default some placeholders, and then replace that placeholders with the real images. Or you can always have the images cached also here. Then instead of having multiple different images, you can combine all images for these specific requests in just one image, and then through CSS show the specific image to the browser, so you can have that. So that's a very important thing. So there are multiple ways of optimizations that you can have. You can even compress the data, compress the return response, like you can use the gzip to do that. There are multiple different compression algorithms that you can use. All of that you can configure, all of these. So then you can combine, as I was saying, images into just one image, and then through CSS show the correct image in the right place. So there are multiple optimizations that you can do here. Now, if there is no cache, so in here it will forward to data center A, or it could forward to the data center B, depending of the way that you have the CDN configured, as I explained before in here. So then let's say that the data center you have, well, in this case, so this is for the CDN, this is like, so you have this CDN for US, which all these data centers will be also in US or around or close by. And then you have here the CDN for UK, where you have all of these data centers in UK ideally, or some other place in Europe, whatever. It could be all of these, it could be in AWS to be faster or not, so independent of this. Yeah, so you have the data centers A, inside of the data centers A, then you can have Nginx as the first public layer, and this based in the URL, it will redirect to the right internal, so base URL redirects to internal servers architecture, where in here you can have an LA with LB with multiple servers related with articles, so everything, so I was saying articles, so to products, so all these requests goes to one LB, maybe this goes to another LB, so this for products, then you have this is related for the users, and this is related for the payment, something like that, where automatically the Nginx, you need to configure Nginx to check if the URL is /product/ whatever, or just /product. You can do that through regex, forward this to the LB IP whatever, or you can have a specific domain, internal domain, then it is related with the specific LB. Then if you do another rule in the Nginx saying if URL contains the user, goes to another LB, otherwise if it is cart, goes to other LB, blah blah blah. And when it gets here, the products, what we'll do is when it calls this, then this specific products, what we'll do is the LB, then you'll have, like if this will be like in Java, like the example, you have the Tomcat server, where the Tomcat, it is a web server that will read that specific URL and will forward that to the specific controller. So I'll advise you to have the MVC type structure inside of your app. So you should have the controllers should talk with the services, the service should talk with the repositories, that the repositories will have the models or the record type, like in Java now you have, or we can call it the entities, now it's the record in Java, the Java 17, but just to don't make it confused, let's just leave it here, model entity, and then the repository, it could be Hibernate, GPA, something like that, or it could be iBatis if you want, Well, basically it could be a ORM system, like Object Relational Mapping system. Then you could have the model which should be DTO, that then all of this, then when you create the model and you mix it with the GPA, then it will make it a DAO. So you can put it here, a DAO, data access object, where basically is a DTO but with functions that allows you to insert, to interact with the database. Model service repository, model. Yeah, so this is usually this is the basic thing that you should have. At least you should have like these 4 layers. Obviously that's in here. Before that you should have a routers layer. Between all of these you should have cache systems also. Yeah, and then from here that's when it connects with the database. Well, in this case here is like the database connection is through the repository, but it's fine. But so this is just so you can get the main idea in here. So the same thing here. Now all of these should have cache, so all of these you can talk with Redis. So you can have a TCP connection, so you need to have the correspondent library to interact with Redis. So then you can simply just call the correspondent functions to cache a specific result through a key, and then you put the value, and then you do the set cache, and then to get it you do the get cache, where you pass the key, the correspondent key, and you get the cache. And you get the cached value. Then you can always check if it is valid, if it is not. You can have TTLs in here also to be sure, but that is inside of your logic. This is just so you don't need to so more lower you go in these sub layers, more latency that you have. So the idea is to have less latency so you can have the request much faster. So that's the main goal. So in order to do that, if you have in all these sub layers, if you have cache, it's always better. So then you can have then you can simply, instead of calling the sub layer, you can just call the specific cache and you can just return the cache. So all the process just go up to the above layer, so until it gets to the client. Okay, so this is an example. So let's see that for the card. So let's say that in here the card servers you have a function to make some payments, where they basically will put some the credit card information, or they'll call PayPal, whatever. So but you don't want these to be synchronous. Well, there are some cases that you might want, so you need to analyze if you want the payment process to be synchronous or asynchronous. In case of if you decide to be asynchronous, well, and even if it is synchronous, you always have other actions that will be asynchronous, like sending the email, saying that the payment it was successful. So there are always multiple ways of doing this. If the payment is asynchronous, then you can always have here a process here inside that can have like threads, and then at the end, let's say that you want to perform multiple different actions, and then you can make multiple the corresponding payments. So let's say that you want to make the payments, but additional, before you make the payments, you want also to get a temporary key, or you want to, let's say that when you do the specific purchase, let's say that you want to create a specific hash that you'll need to return to the client. So the client, through that hash, let's say they need to return some password, whatever, and with that password the user needs to put in that password to enter in some other type of system to have access to. So instead of doing this sequentially, you do the payment and then you do the request to get that specific hash. I'm thinking that the logic to generate that hash, it will be in another server. So instead of doing these two requests synchronously, that will be blocking, you could do this asynchronous. So you could do the payments, you can put the payment in a worker, so you need to configure this, you need it to be like the Kafka or Amazon SQS, whatever. You need to connect this, you need to register the specific worker, you needed to have a listener here, so then it could process the correspondent payments internally or calling a third-party API like PayPal, whatever. And then when this gets processed, this listener could trigger some other threads that you generate here. So let's say that you create here 2 threads to parse that 2 requests simultaneously. So then you can have, when it gets here, so basically you create here a blocking. There is a barrier, if I'm not missing, I believe that the name is a barrier. Well, you have the cyclic barriers, you have blockings, you have semaphores. So I'm not remembering now the right term, but basically you can block the specific threads. Let me put here. So this is one thread. You can basically blocking the thread until you unblock it, and in here you unblock the threads, basically. So then the code in here it can continue, and then at the same time you launch another thread that will generate the hash, whatever, or password, or some password, whatever. And then at the end you do the wait, and at the end, when you get both responses from both threads, you can return the response. So this is just an example. So this depends, all of this depends of your needs, of your logical business requirements. You need to analyze each different situation. And let's say that after this, let's say that this then sends an email. In here you also create another worker for SQS that will have another listener that then will send the email through SMTP, whatever. So there are multiple ways of you can do this. So what I'm explaining to you is ways of having parallel processing, that so you can have much faster responses. So then the response can return to the correspondent client. So in here, so let's say additional, so before this, probably if you are doing a payment, you need to make some checks and some requests to the correspondent database. You can have cache also in here, in the cart, in these requests. Then also you can have you can have the Redis, talking with Redis. Additionally, if you already, let's say that you generate this hash in order to, for the next request, instead you can cache this in Redis, or you can cache this if you want to have a more structural data. Maybe you want to save this in some JSON type of data. Let's say that the user generates for each product that he buys, or each service that he's buying, it generates a specific hash. So you want to have a relationship between the hash and the specific service. That should be inside of the user details. So that is like, imagine this as a JSON structure where you can have all this data structure in the right way, and then you can save this to MongoDB, so next time you can fetch this much faster instead of being in Redis. So Mongo is more a persistent database storage. So more, what do I need to explain you more? Okay, so this is just an example, but still this was an example for an e-commerce website. And additional, of course, that's, let's say that now you have, then in here you could have your own database environment, where in here you could have multiple different databases, also master slave, whatever the structure that you decide to make this structure faster. But now let's say that the data that you have here, maybe you only have here the data for the data center A is for US, and so A, B, C, D, and here is the D. Yeah, so in here you have the database with the products for US only, and in the data center C and D maybe you have another database for the products for the UK store. This is another way of doing it, or if you want you could do something else, which is instead of doing this, instead of having this, you could have all of this talking in. If you have a multi-tenancy application, you could have all of this talking in just one centralized database, which could be synchronized. So instead of having this product separate, you could have in here you could have something like this if you wish to, where these both the database environments, it will be always synchronized. That's one way of doing that, depending of the admin panel. If the admin panel is only accessible through this data center, it should be no problem. However, if the admin panel for US can always be accessible also through the data center C, in this case you can insert products in the US market from here. In this case you need to be careful with the synchronous latency for here, because when the US user sees the markets, they will see the US markets from this database. So that's one way of having the things, which is not very good, because let's say that you have a user that is UK but he wants to see the e-commerce store from US. So or you can do this through user interface, where in your e-commerce sites you have a place where you can select the store. Like I can give you an example. So Amazon does this. Amazon does this. You can select the Amazon from Spain, the market from Spain, the market from UK, the market from Germany, the market for US. You decide that independent from where you are. Or you can have something that does this automatically for you, which was the case that we explained before, based in geolocation. Of course, that always you can always from here you can always forward this. You can always check if there is some cookie forcing that specific store, and then forward this in this CDN. You can always forward this to the CDN from UK. So let's say that if cookie for the store, the e-commerce store exists, we can always forward this to the CDN from UK. You can always have this type of configurations in each CDN. Also, there are multiple ways of doing this, but my point is, for the databases, you can always have all the databases stored in just one place, so a centralized storage system, which could be like RDS or DB, Amazon, whatever, which is MongoDB. So MySQL, MongoDB, or any other type of storage. You can only have maybe just one centralized, where contains all data from all e-commerce stores from US, from UK, and whatever the other stores that you have. And then automatically all these servers here, instead of calling an internal database, will call this external database, which it's always possible. So the connections to a database, they are safe, so that's fine. So you don't need to worry about any TLS and things like that. So it's fine. So you can always, what you need to be concerned is about latency, because you need to be careful if you are in US and if you have your data center servers in US and you are requesting something from UK. Let's say that this centralized database it is stored in Europe, and you are requesting this in Europe, you have a little bit of more latency. So when I was telling you that so these 100 milliseconds, 300 milliseconds, this is if you have these milliseconds are based in the intercontinental requests. So basically between US and Europe, you have physical cables underwater that connects both continents. The latency latency of a TCP requests between both continents is between 100 milliseconds to 150 milliseconds, if I'm not mistaken. Then you have the satellites thing, like the Starlink, if I'm not mistaken, Starlink. Yeah, the Tesla satellite thing. So basically, the latency of this connection is much lesser. However, the bandwidth, it is much lower. So it's not only the latency that you need to be worried about. So when we are talking about speed, we need to talk about latency, we need to talk about bandwidth, we need to talk capacity, we need to talk about speed, we need to talk about performance. So all of these are different things. So through my professional experience, I can tell you that I've been talking with a lot of people that they confuse a lot all these things. So latency is milliseconds between two endpoints. Simple as this. If it is a TCP, if it is a ping, well, in this case, this is when I'm saying this latency, this is for the ping. If it is a TCP, it's a little bit more, because TCP is 3 connections, ping is only 2, is round robin. Then you have the bandwidth. Bandwidth is the number of bytes you are transferring. So you can have, so if you don't have enough bandwidth, it means that you need to make more than one request. So it means that the latency will be not just 1, it needs to multiply for 2. Let's say that in order to transfer an image, you need to make 2 TCP requests. So it means that the latency, instead, if you don't have enough bandwidth, which happens in here with the Starlink, you need to make 2 TCP requests. Instead, if you have intercontinental cables, if you have enough bandwidth, you just make 1 TCP request to get that specific image. So you need to worry about this. So bandwidth, it is important also. Then you have capacity of the server. This we are talking about hardware, about CPU, memory, thing. This will influence the performance. So performance, we are talking about how fast can you deliver some logic, or deliver or create response logic, something like that. Create some response logic. So this is the performance. That's where it enters here the cache. The database connections, the TCP keep alive connections, where when you have TCP, you just waste basically. You just need to do the handshake once, and after you have it handshake done once, you can reuse these TCP connections. Usually, and by the way, when we are talking about HTTP, we have 2 types of HTTP. We have HTTP 1.0 and 2.0. So the 2.0, it means that after you do the first handshake, all the rest of the connections, you don't need to do handshake anymore. You just do the request and you get directly the response with the correspondent data that you request. Similar as the ping. So as I was explaining here. Okay. So this is the performance, and then you have the speed. So the speed is basically the total number of all of this. So it's the calculation that you do to be sure that how long it will take this request to arrive to my site. So this will be request time. request time response, something like that. Now, and in here, so the capacity, so this is very important because this is where it enters the load balancers, that's where it enters multiple servers, just one server. That's where it enters the server architecture to have as capacity as you can, so then you can have a good performance, you can have all the resources from the server able and be available to perform the action that the client requests to the specific server. So then you can have a good performance, you can return as fast the response as you can. So then you can have all of this a maximum speed. So it is very important to understand this. So why am I saying this? This is very important because when you are talking about a centralized source system, and sometimes I talk with people that they get confused about this, which is it's not a bad idea to have a centralized source system in just one place. There is no problem. US makes requests to UK, like we are talking about 150 milliseconds of delay. After the TCP is done, you have good bandwidth, and we are talking about if you are not sharing huge amount of data, if it is just a simple data, you can do this. Although you can always then cache some of these results in your server architecture. So let's say that in the case that I was explaining, so let's say that you don't have any individual databases in each data center, but you have then another data center here, let's call it data center E, where you have a centralized database. Let's say that you have this case. So if when the data center A or the data center E, well, either A, B, C or D data centers, when they make a request to the database, they will make a request to a database that is not in their own internal structure, and that's fine also. There is no problem with that. We need to analyze the latency and the speed of that. If you are not getting huge amounts of data, it's still fine, because then you can store that data in here. So as I was saying, before you call the specific database, you have cache systems in multiple different levels. So when you get to the database call, then you call the centralized database, and then you're gonna store the correspondence results in here in cache to be faster for the next requests that other clients may do. So that's fine also, because the latency is not a huge latency, so that's also a valid architecture. So all of these, I'm not saying that this is the best solution. What I'm saying is that this is also a solution that we need to analyze. So you can have multiple different databases in here, or you can have a centralized database, and you can even have the three, where all of them they are sync. But attention, because more complicated is your server architecture with synchronized syncs, more difficult it is to handle, more risky it will be, more bugs you have, more problems you have, more headaches you have, more unstable your system be, and this reflects then to your business, because then your business will be unstable, and it will be, you end up expending a lot of money unnecessary, because you architecture and because you plan wrong your database server architecture. So it's very important that you need to analyze each requirement of what you need to do, so then you make the correct decision. So it's very difficult, I tell you, oh, you have an e-commerce website, and I have products, I have a store in US and I have a store in UK, I have products in US, I have products in UK, I have products in China also, and so what is the structure that I should have? It depends, so we need to analyze a bunch of constraints. It depends of the architecture, it depends of the languages that you are using also. So there is a bunch of key factors that we need to analyze and to make a good decision. Also, we need to make also tests. We need to make tests to be sure that the latency is still fine. Don't forget that you just need to have your website ready in between 2 to 3 seconds. So where did I put that? So that's the standards. So your e-commerce websites needs to load in 2-3 seconds, and this is not only server architecture. So it is, and this is something that everyone needs to understand. It doesn't make sense. You have a huge and enterprise server architecture with a bunch of CDNs shared across the roads, a bunch of data centers with a bunch of load balancers, a bunch of auto-scaling servers, all of that. It doesn't make sense to have that if you don't have your application logic code well structured. So if you don't have this well structure, it doesn't make sense. And additionally, also, it doesn't make sense even if you have this correctly, but even if you don't have this structure in your database correctly, it doesn't make sense. So you need to be worried about not the caching, about the views, first you need to have a good structure. If you want to have a multi-tenancy website, a multi-tenancy e-commerce store is not a normal e-commerce store. You need to have the database structure prepared for that. And then you need to have all your logic code needs to be prepared for that. If you have only synchronous processes, it will be much slower than you have asynchronous processes. However, the asynchronous process is much more complicated to manage, obviously. So you need to analyze all of these to analyze what you are able to don't go forward in order to have more stability instead of speed. You cannot have both. So this is things that you need to analyze to decide what is the best structure that you need to decide here. So let me put here a very simple overview of when you are defining application structure, when you are planning all your applications, what you need to have, what are the key factors that you need to pay attention. So we're talking, we need to have hardware, we need to have networking, we need to have distributed systems, we need to have the application codes, then you need to have DB. Like in a very high level saying this is. So first of all, you need to have your database with the correct data structure ready for your requirements. You need to have this prepared. I'm not talking about optimizations, I'm talking about the database tables diagram. So you need to have that with the correct structure. The data needs to have the right structure. Then you need to make a decision if you want to have a SQL or a non-SQL database, a relational or a non-relational databases. You need to analyze for each individual database, you need to analyze what's faster. I can tell you that SQL Server, if you have relational diagrams with foreign keys, it's much slower than MySQL. If you don't put SQL Server with foreign keys, it is much faster. So there are a bunch of things that you need to analyze here, you know? So that's the first part, database. You need to analyze this very careful. There are a bunch of key factors that you need to analyze here. Then application code. This is the logic code. You need to have these codes very well structured. And this application code, it divides in front-end and back-end codes. This is another thing that some people sometimes have some trouble to understand this. So the front end needs to be optimized with the back end, as I was explaining. So instead of making multiple requests to get, let's say that you are showing a list of products, instead, and each product will have an image. Let's say that you want to make a request to get the products. Then when that data, let's say that the front end, instead of the UI get parsed in the back end, the UI can be parsed in the client side, so it doesn't overload the backend, so the backend can be faster. Let me give an example. In PHP or in Java, when we are working with JSP, all the front end is parsed from the backend. Then the front end, the browser, it will show that final results to the user, and based on that, then we'll check if they are JavaScript files, CSS files, image files, and we'll make other TCP connections to our server to get that binary files for the images and to show that specific images. This is an example. Binary files, if the images, if they will be binaries. If there will be SVG, there will not be binaries, of course. This I'm just showing you simple examples of this. So in that case, so instead of having to parse this in the backend, if latency is an issue for you, you can have something like React or similar apps like React, where basically you in the backend only returns the data, and that data could be returned in a JSON format, and it should be compressed with like the gzip library. So it will be the bandwidth, so the length of that data be smaller, so you don't need to use too much bandwidth of the network, so the latency, so you can do less TCP requests, so you can have more faster, you can have less requests and faster requests, you can get that response faster. So these are optimization that you should do in the backend. Then the front end automatically it will decompress that information, and then based in the JavaScript that has here, or based in the logic that the front end has, it will create the UI logic code to show. So in the products, it will be the front end that will show the list of products. So the backend is only responsible to show to return the list of products in raw data. Additionally, why, if you are only showing here the image, the name and the description, you don't need to return other type of information, like when was the product created, how many purchases it has, how many comments. If you are not showing that, it doesn't make sense. You are just basically using bandwidth unnecessary, which will increase the latency. So all of this, you need to think about this very careful. So all of this needs to be done very well. Additionally, then the front end will to create that specific, if it is in the browser, that specific HTML that will show in the browser. But now let's say that even the front end shows we have 5 products and is showing a list with 5 different images. What then the browser will do? After the front end shows that specific HTML, the browser will execute 5 requests, 5 TCP requests to the server to request that binary independently. We are talking about 5 TCP requests round robin, so we are talking 5 multiplying by, depending if they are not cached, whatever, by 300 or 150 milliseconds. So this is latency. So instead of doing this, you could have all the images together, so you can only make 1 TCP request, and then after you make only 1 TCP request, then it will be the CSS that will show that specific images in the right placeholders, in the right places of the lists. This is like you just do 1 TCP request. This is like things that you need to optimize. This is like front-end and back-end optimization. So this is in the application code, and I'm not talking about cache. I'm not talking this about getting the image from cache, even if the client instead of requesting this to the server is requesting this to CDN. Okay, but even if it does 5 TCP requests to CDN, still like it's 5 requests. Why not just do one request? Because maybe instead of having 2 CDNs, one in US and one in UK, maybe you can have one centralized for all the roles. You'll see that for most of the cases it will be fine. Seriously, it will be fine. Like, so all of these we need to analyze, and we need to do some tests, and we need to analyze carefully. And then we go to distributed systems. Distributed systems, when we are talking about CDNs, load balancers, to multiple servers, instead of servers talking with servers, with different protocols, all of that. So we need to analyze. For some specific cases, you don't need to have an enterprise server architecture. You don't need to have that. You can simply have a simple system where basically you just have a few servers where you have a good cache with CDN or without CDN, because they are, if you have this in Amazon or if you have this in some other hosting servers, they have very good latency and very good speeds. So for most of the case it will be enough, and you don't need to have a very complicated distributed system. Don't forget that if you put this in Amazon, Azure or GCP, Google Cloud Platform, like the budget, it will be huge for you. You have a huge budget, you know? And if you're not a guy that does a lot of campaigns, that you wanna have in some specific cases a lot of hits, suddenly a lot of hits in just 1 hour, and you need to have auto scaling and things like that. If you are just a normal e-commerce website, sometimes maybe you don't need auto scaling. Maybe you just need to have a normal hosting service where you talk with them and you're gonna tell them, hey, attention, because during these hours I'm gonna have a peak of users, so please be careful, so prepare your server infrastructure to have this ready, and they'll automatically, they will have that. There are services that do that. You don't need to be you to manage that in AWS. It will be much expensive for you. So all of this, I'm not saying that this is the right solution. I'm saying that all of this we need to analyze carefully. Okay, this is for distributed system. Then network. That's what I was saying, that requests across continents is not such a bad thing. That's latency, like TCP request, well, ping request for intercontinental requests between 100 and 150 milliseconds. TCP requests, where first you do the handshake is around 200 milliseconds, but then each TCP connection we are talking about 150 milliseconds. This is between continents. Like if you have the requests in the same data center, obviously that the latency will be much lower and the requests will be much faster. But let me ask you something, is that worth it when you have a simple system and when basically then you need to have a huge team behind you to manage all the problems that this big server architecture it will create? Because only if you really need it, that's when you should really have it. Not just because I think that, oh, it's cool, or no, I think that I need it, but you didn't even test the simple server architecture. You didn't even test the other distributed system with other hosting companies. Maybe it will be enough. It's less work than that you have from your side. You can decrease your team. You're gonna have less team players, you know, like you're gonna have less people working for you, and it means that you will expend less money. At the end will be a much cheaper service altogether, which means that then you're gonna have a bigger profit margin, and then you can have better prices also, which then will bring more clients to you. So all of this involves all the business logic too. So it's not just because, oh, we are growing up, now we need to have this prepared as an enterprise infrastructure. No, maybe you don't need that. What you need maybe is to reorganize this part, and maybe you need to check the database structure. Maybe you don't need anything of this, or you still need this, but you will need this in a much simpler solution. So then we're talking about network. Network is exactly that relationships between continents, same data center, multiple different data centers talking together, CDNs, everything, the latencies between them, and then we have the hardware. The hardware is, even if I decide to have distributed systems, which type of servers do I need in my internal server architecture, in my data center? Maybe I can have a simple server, which is much cheaper, or where I can have a load balancer where I have 5 servers that are very cheap but are very they are enough to execute my logic. Or maybe I can have just one server or two servers, very heavy with huge memory, a lot of CPUs, a lot of cores, all of that. So we need to analyze all of these things. And additionally, then we need to learn how to fine-tune, and in here in the hardware, you need to learn how to fine-tune the OS also. So what this means? So we need to fine-tune the number of threads that hardware can process. We need to fine-tune so let's put here maximum threads. We need to fine-tune TTLs for TCP alive connections, TTLs for session sticky. Well, why this is important? So all these TTL TCP alives, it will be important because when you make a TCP connection, when you are connecting the servers to the database, when you are connecting the servers to Redis, when you are connecting the servers to your SQS or RabbitMQ, whatever, or to MongoDB, when you are making these connections, the TCP is alive. Now let's say if this is not TTL, if it's not synchronized, what you're gonna end up having, it will be that from one side the TCP connection will be killed, but from the other side you'll not know it. So this is what calls the stale or half open connections. So in order to avoid this, you should have pings and get times from this endpoint. So let's say so specific for this, and then we'll return here again. So related with this, so let's say that the server connects with the database. The database has a different TCP keep alive TTL. In that case, let's say that MongoDB closed the connection, but in here in your logic codes, let's say that in your logic code it already it didn't receive that closed connection, so you think that you still have that connection. So the connections that you make here, they'll need to be in the thread pool, all the connections. So what you need to do then, you need to have an external service checking that connections pool, if that specific thread, that specific connection, that specific TCP socket to the database, if it passed a certain amount of time, the server here needs to make a request to MongoDB, a ping, to be sure that this still be alive. But still, the ping sometimes returns that is still alive. So instead of making a ping, you can also request what is the time, the current time of this MongoDB. So all these servers needs to have the same needs to be configured with the same time. If today this server, if it is 2 p.m, in this server needs to be also 2 p.m. So when you request the time here, after it passes a certain amount of seconds, so this type of processes runs asynchronously on a parallel layer to check if, imagine this as like a cron job running as every 5 seconds, where in here basically it will ping every 5 seconds to check, well, it will run every 5 seconds, but we will check the thread pool, and it will check there is any connection that it wasn't executed in the last 5 seconds. If there is, so then do the ping and get the time to the current MongoDB to be sure that this is still alive, and then compares that with the current time that we have, something like that. We're not talking about milliseconds, so we don't need to be worried about synchronizations of milliseconds. No, this is like seconds. You can do this based you can always do the cron job based every second, but still you can always do this based in 5 seconds. Or you can even still do this constantly. You can have thread pools that you make the requests here, okay, it is alive, okay, next after it passes all the connections, it starts over. All the connections, it starts over. All the connections, it starts over. Still, you are overloading the database. Like, so all of this needs to be analyzed carefully to make the correct decisions. So, in my point of view, 5 seconds, it is enough. Why it is enough? And your question is, okay, so what happened during that, in the middle of that 5 seconds? Let's say that in the middle I receive a request here, I make a request with that stale connection to my database, and I don't get any data. So in your logic code, you need to have that prepared for that also. So if you have, in case that happen, you have your logic code prepared to catch that exception, and then to execute, to trigger that cron job or that other service that the cron job also uses, that will check all the TCP connections, and that will return a good and active TCP connection to you, so you can make the request again to Mongo. That only happens, of course, after you check if there is no cache. So if you do this, the service will be foolproof. But you need to have all this. So the logic, as I was saying, you need to have your application logic prepared for these things. It's not only fine-tune the OS, you need to have your logic needs to be prepared for all of these things. That's this part here. Otherwise, it doesn't make sense to be thinking about this. You need to have, the most important part is this. The most important part is this, is the database. Then the second most important part, it is the application code. And then is the distribution systems, and then is the network, and then is the hardware. Well, between these two, maybe we can flip, you can switch these two. But still, like, this is the sequential order, so you can have in mind. So, after that, as I was saying, you need to have the OS fine-tuned correctly. With the correspondent TTLs, with the session stickies, configured correctly, with all the web servers configured correctly. Also, you can have caching automatically based in URLs, based in service, whatever, if you want to. This can be configured in the web server also. More, you can have multiple different things. You need to be careful about TLS and MTLS. Don't forget that, as I was saying, clients, CDN to web server, well, CDN to your data center, that is inside of your data center, web server to multiple different load balancers according with the URL, and then each load balancer to each server. If you have MTLS, you need to have for each interaction you need to have a specific MTLS for individual ones. Instead, you can have simple TLS. Okay, you want to have a huge encryption, you can have something else, which is you can have still the TLS, so it can be faster across all these layers, across client, CDN, web server, load balancers, and then servers. You can have the TLS, where all of these don't need to have the pass-through as you need to have in the MTLS. But additionally, then you can have, if you want to have really security, you can have in your clients, you can have a public and private key that encrypts or decrypts the information, and in your server side you do the same thing. You have also private and public keys, or in this case you have public keys in your server sites that will encrypt the data, and the client side will have the public key to decrypt that data. But the public key, it will not be shared across the network, as happens in the TLS, as it happens in the HTTPS, as it happens in the SSL. No, in this case what I'm saying is that if you have, in this case, well, it wouldn't make sense if you are if you have a browser, but if you have an iOS and Android's native app, maybe you can put there a public key, so you can have another layer, another encryption layer for sensitive information over the TLS. This is just a simple example that I'm showing you. Okay, and I'm sure that there are other fine tunes that you always need to do here. You can configure the post length, the maximum post length. Also, you can configure the maximum variables that you pass through the requests. Also, there are a bunch of configurations that you can do in your web server. So this is more specifically for the web server. So there are a bunch of tuning things that you can do. So basically this is like for related with OS, hardware, software. OS it is software, but okay, but I believe you understood what I was saying. Let me give you here another example. MTLS, it could make sense if you have specific CDN caching results only specific for specific clients, and I can give an example. So the NFL mobile app or any app where you have video on demand, where you need to pay for that video, you need to have a unique URL to see that video. That unique URL will be created based on the payment of the service, based on the payment of the video that you purchased, that you bought. So that URL can be cached in the CDN based in MTLS, because MTLS knows your unique identifier. It's you, it's for that client. So you can, for that request, for that URL, you know that you're gonna get back another URL specific with that video, or specific with the token that allows you to see that video. So that's another thing that you can do, that you can use MTLS. That it could be an interesting way of using MTLS. Otherwise, if you want to have speed instead of security, in that case, so you need to analyze that better, because instead of using MTLS, maybe you should use TLS. This is just an example. And in here I was putting here, but now then I forgot to add here. So you have another layer, which is the security layer. Encryption. You can create your own encryption algorithms, you can use public private key, whatever. You can use a bunch of different algorithms that already exist, multiple ways of using encryption layer. Be careful, because sometimes the encryption gets messy when you zip it. So there is a bunch of factors here, but all of that needs to be analyzed according of each individual requirement. So because more complicated things that you put, more difficult it is to manage, more people you need to have, more complicated will your system be, more unstable will be your business. I'm not talking about the system also, but then your business will be unstable. People will not like to buy things in your store, you'll lose clients. So that's not what you want. You want to have, the main goal here is to have a stable system. Then after, you want to have speed. First stability, then speed. That's in my opinion, that's my advice to you. So basically in a global scope, I believe I covered most of server architecture. Sorry to be doing this in a text file. I could have done this better maybe in a diagram form. It's just because here it's easier. I hope you could understand, and let me know if you have any other question. So thank you very much.